Good morning, everyone, and welcome to today's presentation. I'm excited to share with you our study on the effect of concentration on the rate of reaction. The focus will be on the reaction between sodium thiosulphate and hydrochloric acid. I'll be guiding you through the key concepts, the experiment we conducted, and what we discovered about how concentration impacts reaction speed. Let's get started. Today, I want to talk about our main goal for this experiment, which is to study how the concentration affects the rate of reaction. Specifically, we're looking at the reaction between sodium thiosulphate, or Na₂SO₄, and hydrochloric acid, HCl. The key idea here is that by changing how much of each reactant we have, we can see how quickly the reaction happens. This helps us understand the relationship between concentration and reaction speed. It's a fundamental concept in chemistry because it shows us how reaction rates can be controlled and predicted. Throughout this presentation, we'll explore how different concentrations influence the rate and what that means for real-world applications. So, this slide sets the stage for understanding the core purpose of our investigation. Let's start by looking at how the rate of reaction depends on concentration. As you increase the concentration of reactants, the reaction usually speeds up. This is because there are more particles colliding more frequently, which increases the chances of successful reactions. In this experiment, we focus on the reaction between sodium thiosulphate, Na₂SO₄, and hydrochloric acid, HCl. When they react, sulfur is formed as a product. This sulfur isn't very soluble, so it makes the solution turn cloudy or opaque. This cloudiness is actually very useful because it allows us to measure the reaction's progress visually. We mark a specific point, an X on the solution, and as the reaction proceeds, the sulfur forms and the cloud spreads. The time it takes for the X to disappear, meaning the solution becomes clear again, tells us about the rate of the reaction. So, essentially, by measuring how long it takes for the X to vanish, we can determine how quickly the reaction is happening under different conditions. This ties back to our overall theme of understanding how factors like concentration influence reaction rates. Let's take a closer look at this chemical reaction. Here, sodium thiosulphate, Na₂SO₄, reacts with hydrochloric acid, HCl. The reaction produces sodium chloride, SO2 gas, elemental sulfur, and water. An important thing to note is the downward arrow next to sulfur, which indicates that sulfur precipitates out of the solution as a solid. Now, when we talk about the rate of this reaction, it's inversely proportional to time, meaning as the reaction speeds up, the time taken decreases. This kind of relationship helps us understand how quickly reactants are converted into products. Connecting this to our overall theme, understanding the reaction mechanism, and rate helps us control or optimize processes in industries like photography, water treatment, or even analytical chemistry. The key takeaway here is recognizing how different reactants interact and how reaction rates can be expressed mathematically to give us better control over practical applications. Let's take a closer look at some of the essential apparatus we use in the lab. First, we have the conical flask, which is really versatile for mixing and swirling liquids without spilling. It's a staple in many experiments. Next, the stopwatch is crucial for timing reactions accurately, ensuring precise measurements of how long processes take. The measuring cylinders are great for measuring liquid volumes with accuracy, which is vital for reproducibility in experiments. The beaker, while more general, is useful for holding and pouring liquids, especially when exact measurements are not critical. Now, you'll notice there's a paper with an X mark on it. This often indicates that something is not suitable or should be avoided, maybe a particular method or material. Lastly, the apparatus as a whole refers to the collection of tools we use to carry out experiments effectively and safely. Connecting all these points, it's clear that selecting the right apparatus is key to obtaining accurate and reliable results in our experiments, which ties back to our overall theme of precision and careful scientific practice. Let's take a closer look at some of the chemicals we'll be working with. First, we have sodium thiosulphate solution. This is a common reagent in chemistry labs, especially useful in titrations involving iodine. It acts as a reducing agent, helping us to determine concentrations accurately. Next is hydrochloric acid, which is a strong acid often used to react with various substances in our experiments. It's important to handle it carefully because of its corrosive nature. Lastly, we have distilled water. This is pure water that has been purified through distillation, ensuring no impurities interfere with our reactions. Using distilled water helps us maintain the accuracy and reliability of our results. These chemicals are fundamental to the procedures we'll be discussing, and understanding their roles is key to grasping the overall process we're exploring today. All right, let's walk through the procedure step by step. First, draw an X on your paper and carefully place the flask on top of it. This helps us keep everything in a consistent position for the experiment. Next, add 10 milliliters of sodium thiosulphate, or Na₂S₂O₃, into the flask. This chemical plays a key role in the reaction we're about to observe. Then, add another 10 milliliters of hydrochloric acid, HCl, and immediately start your stopwatch. It's important to start timing right when you add the acid, because that marks the beginning of the reaction. Now, gently swirl the flask to mix the solutions well. Gentle movement ensures we don't introduce any extra variables into the reaction. Keep an eye on the solution and note the exact time when the X disappears from view. That moment indicates that the reaction has completed. This step is crucial because it allows us to measure the reaction time, which will be important for analyzing the reaction kinetics later on. Now, moving on to the next part of the procedure. We will repeat the process with different volumes of sodium thiosulphate. Specifically, we'll try 8 milliliters of Na₂S₂O₃ mixed with 2 milliliters of water, then 6 milliliters of Na₂S₂O₃ with 4 milliliters of water, followed by 4 milliliters of Na₂S₂O₃ with 6 milliliters of water, and finally 2 milliliters of Na₂S₂O₃ with 8 milliliters of water. The idea here is to see how changing the concentration of sodium thiosulphate affects our reaction, while keeping other variables consistent. Next, it's important to note that we will keep the hydrochloric acid volume constant at 10 milliliters throughout all these trials. This consistency helps us isolate the effect of the sodium thiosulphate variations without other factors changing. Finally, after setting up all these different mixtures, we'll record our readings carefully. This step is crucial because these measurements will allow us to analyze the reaction's behavior and draw meaningful conclusions about the chemistry involved. All right, let's take a closer look at this observation table. Here, we're examining how the concentration of sodium thiosulphate, or Na₂S₂O₃, affects the reaction rate over time. As you can see, when we start with 10 units of Na₂S₂O₃ and no water, the reaction takes about 28 seconds, with a rate of 0.0357. When we decrease the Na₂S₂O₃ to 8 units and add 2 units of water, the reaction time increases to 34 seconds, and the rate drops to 0.0294. Continuing this trend, with 6 units of Na₂S₂O₃ and 4 units of water, the time extends further to 44 seconds, and the rate decreases again to 0.0227. As we keep reducing the Na₂S₂O₃ and increasing the water, the reaction takes longer, 58 seconds with 4 units of Na₂S₂O₃ and 6 units of water, and up to 90 seconds with just 2 units of Na₂S₂O₃ and 8 units of water. Correspondingly, the reaction rate decreases from about 0.0357 down to 0.0111. This pattern clearly shows that decreasing the concentration of Na₂S₂O₃ slows down the reaction, which makes sense because fewer reactant particles are available to collide and react. This table beautifully illustrates the relationship between reactant concentration and reaction rate, reinforcing the core idea that concentration directly influences how quickly a reaction proceeds. Understanding this helps us grasp the broader principles of reaction kinetics and how we can manipulate conditions to control reaction speeds. As we look at this graph, you can see the relationship between rate and concentration. What stands out is the decreasing trend, meaning that as the concentration of our reactant increases, the rate of reaction doesn't keep climbing. In fact, it tends to level off or decrease. This is a key point because it highlights how reactions can become less efficient at higher concentrations, possibly due to factors like particle interactions or limitations in available active sites. Understanding this trend is crucial for optimizing reaction conditions in industrial processes or laboratory experiments. It ties into our overall theme of how different factors influence reaction dynamics, reminding us that more isn't always better when it comes to concentration. So, as the concentration of a reactant decreases, you'll notice that the reaction takes longer to complete, meaning the time increases. At the same time, the overall reaction rate slows down. This is because with fewer reactant particles available, there's less chance for collisions to occur effectively. The most important thing to remember here is that concentration directly influences how quickly a reaction happens. Higher concentration usually means a faster rate, while lower concentration means it slows down. This concept ties into the overall theme of how various factors affect reaction speed, helping us understand how to control or predict reaction behavior in different situations. All right, let's look at the key points here. First, we see that cloudiness appears due to sulfur. This indicates that sulfur is playing a role in forming a cloudy or opaque solution, which is important when we're discussing reaction progress or the formation of a precipitate. Next, as the reaction proceeds, the substance represented by X disappears, and the solution becomes opaque. This shows that X is being consumed and that the change in opacity is directly related to its concentration. When the solution turns cloudy, it's a clear visual cue that the reaction has reached a certain point. We kept the hydrochloric acid, or HCl, constant throughout the experiment. This control helps us isolate the effect of sulfur or the concentration changes we're studying, ensuring that the rate differences are due to the variables we're focusing on, not other factors. Now, moving on to how we measure the reaction rate, we define it as 1/time. This means that a shorter time indicates a faster reaction, and a longer time indicates a slower one. It's a simple but effective way to quantify how quickly the reaction progresses. Finally, we observe that the rate decreases as the concentration decreases. This is a common trend in reactions. When the concentration of reactants drops, the rate tends to slow down because there are fewer particles available to collide and react. Putting it all together, these points demonstrate how the reaction's visual indicators and concentration changes help us understand the kinetics involved. They also reinforce the overall concept that reaction rates are closely linked to concentration, which is a fundamental idea in reaction kinetics.